Let's quantify reaction rates. So to do this, we need to look at what is called a rate law. The speed of the reaction is the rate of reaction. And so let's start off with an analogy. Let's say that we need to travel to Vernal from Salt Lake City. We're going to check the odometer at the beginning and at the end. And then we can calculate what the rate of travel is. The rate would be the change in distance. So that would be the final distance minus the initial starting point. And then I'm going to divide it by the change in time. And for the change, we use that little delta sign. So it would be my final time subtract my starting time or my initial time. To travel from Salt Lake to Vernal, it's about 300 miles. And just to make our math easy, let's say that it takes us 3 hours. So when I look at the rate, your rate is always going to be some quantity over time. So in chemistry, it's going to be concentration over time. In this case, we're doing miles per hour, but this is a rate. So my average, in this case, we're figuring out the average. My average rate of travel would be 100 miles per hour, but this is a rate of travel. One thing to remember is that reaction rates always have time in the units. So if you ever see a unit that there's time, they are talking about a reaction rate in AP Chemistry. The typical units are molarity per second, which is our concentration per second. So if we did a little demonstration where we took magnesium and put it in hydrochloric acid, you would see a reaction occur. I would have a gas formed, and I would see that my little piece of metal in my acid, it would start to be used up. So what instrument could you use to measure the change in concentration? This is a quantitative measurement. We would want to measure something. Well, there's a couple of things that we could do. We could measure how much gas is coming off, so we could collect the gas. And we could say, okay, we started with 0 gas, and then after a minute, we had so much gas. So you could calculate that rate. You also could measure your length of the metal. So a starting length, and then after a minute, how much is left over. Or you could use the mass. How much mass at before, how much mass the after. And so what we're really doing is we're measuring the disappearance of reactants and the appearance of products. Either one of those could be used to measure the rate of this reaction. So to look and see if the reaction is slow or fast, you'd want to compare it to something else. And to determine if it's endothermic or exothermic, one of the things in the lab you could do is to feel the test tube to see if it's hot, it would be exothermic, and if it's endothermic, it would feel cold. Let's go ahead and calculate the average rate of this reaction. So to find the average rate, you're going to do the change of concentration divided by the change in time. Just like when we did the analogy of driving to Vernal, we had the change in distance over time. In chemistry, we do the change in concentration over time. And it's done the same way. So let's say after 1 minute, my concentration went from 3 molarity to 1 molarity. So I would represent this as 1 molar minus 3 molar. It's 1 minute, so my change in time would be 1 minute minus 0. So I end up having a minus 2 over 1 molarity per minute. And a lot of times they split the molar concentration unit up. So they might represent it as minus 2 moles per liter divided by minutes. And then they rearrange it. So moles is on top and liters is on the bottom, and so is minutes. So they'll do liters to the minus 1 and minutes to the minus 1 in this case. So if you ever see anything like that, just know that they've split up the molarity. And units are very, very important in this unit. So make sure that you're representing those units properly. Another way that you might see the average rate represented is keep the molarity, but then take that minute and put it up above. So they would do minutes to the minus 1. And they may or may not have that little time sign there. It might just be minutes to the minus 1, but the times is assumed. So in this, we have our concentration of our acid. It's getting used up because it's reacting with the metal and making the hydrogen. And so that's why our concentration is going down, because it is a reactant and it's getting used up. So to sum up what I just said before, how do we measure the rate? You measure it by the disappearance of a reactant or the appearance of the product, or both. The concentration is a molar concentration, which is moles per liter. And another way to represent that is little brackets. So anytime you see brackets, that is molarity or moles per liter. Your rate is always positive, but if there is a negative sign, that is just telling you that it's disappearing. So you're more looking at the reactants part. And if it's positive, that means it's appearing. The average rate would be the change in concentration of a certain reactant over time, or the appearance of a product over time. And also remember, when you're doing that little delta or the change of, you do final minus initial values. So looking at this data table, let's calculate the average rate of A and the average rate of B. And this is a very simple equation. So A is my reactant, B is my product, and they should be equal. As A disappears, B should appear. So let's calculate the average rate of A. Unless it's specific, you can just pick the time that you want. Maybe it wants the average from 0 to 40. I think I'm just going to go from 0 to 20. Doesn't really matter. So as far as my rate of A, I'm going to do 20 minus 0 seconds. Remember, it's final minus initial. Of this time for A, I ended with 0.54 concentration minus 1. So doing my math, I get a minus 2.3 times 10 to the minus 2. And my units are meters per second, because that's my molarity is on the top and I have seconds on the bottom. We can do the same thing with the B. And again, I'm going to use the same time. So I have 20 minus 0 seconds. And then I have 0.46 minus 0. Because when we started off, we had no concentration. And when I do my math, I get 2.3 times 10 to the minus 2 meters per second. And that makes sense here, because as A disappears, B will appear. Here is a molecular view of A turning into B. So we first start off with A in my container, and then we see as time goes by, more and more B appears until we get our mixture of gases that's at the end. We can also graph this. So we can see at the start, I only have A. And as time goes by, A decreases its concentration. And that's because it's getting used up and turning into B. And we see that we start with B at 0. And as time goes by, it increases. At this point, they just happen to be equal to each other. That doesn't mean anything. But at the end of our reaction, that we see that we have more B molecules than A molecules. In your packet, you can stop this tape and do a problem that is similar to finding the average rate. And it might be 10 or it might be close to number 10. So find one that is more appropriate and matches this. Let's look at something that's called the relative rate. In relative rate, you compare each reactant to other reactants or to the products. And you set it up by looking at the coefficient and taking the inverse of the coefficient. So looking at magnesium solid, this is my reactant. And I know it's going to disappear in the reaction, so I'm going to put a little negative sign. And then I'm going to do the change in the concentration of the magnesium over the change in time would be equal to its other reactant disappearing, so negative, but half of it. And that is because of that 2. That means that the HCl will disappear twice as fast. So if I'm putting them together, then I take the inverse of that coefficient. But it's going to look the same. I'm going to do the change in molarity of the HCl over the change in time. And as far as my products go, they are going to appear. And so you can put a little positive if you want to, but you don't need to. The hydrogen gas that's formed is just a 1 as far as balancing it. So I just do the change in concentration of the hydrogen gas over time, and that is equal to the change in concentration of the magnesium chloride over time. So this is the relative rate. So we see again the reactants are disappearing and your products are appearing. So the sign just tells you which direction that they're going. But these are a relative rate. So if I knew the concentration of my reactant and I knew my change in time, I could calculate a product, the rate of its appearance. You can calculate the instantaneous rate at any one point in time. This is more of a calculus type problem. And maybe you've talked about this in a calculus class if you've taken that. That is beyond the scope of AP Chemistry. So let's look at a reaction where we can apply this average rate formula where you take the coefficients and make them the inverse as shown in that last slide. So let's look at this balanced equation. So we have 5 moles of bromide ion, and then we have a bromate ion, and then we have a hydrogen ion, and that yields bromine and water. And I have a 5:1 to 6:3 to 3 ratio. This problem is a little bit more complicated because the coefficients are so large, but hopefully you can grasp what's going on. So we are given the bromine, so I would write that as the change in concentration of the bromine over the change in time is equal to 0.039 moles per liter per second. So let's look and solve these problems. So at what rate was water being formed? So now I'm going to compare the water to that Br2. So I know that 1/3 of the change in the bromine divided by the change in the time, that would be equal to water is 1/3 the change over time. Now these are both products, so they both are positive. But that is how I would set up the problem. So this portion right here is this number. So I can plug that in. So I have 1/3 times the 0.039. That would be equal to 1/3 times what I'm trying to solve. And I would multiply each side by 3. So those 3's would cancel. And my final answer, and I kind of don't have room to write it, but I would have this equal to that rate the water's being formed. And you can probably think through that because they're both at a 3:3 ratio, or really 1:1 ratio, equal parts, that they would be formed at the same rate. All right, let's do the next problem. So at what rate is the bromide ion being oxidized? So this time I am comparing a reactant that's going to disappear to my product that is going to appear. So make sure you use those negative and positive sign just to show the direction it's going. So I'm going to have a -1/5 of the bromide ion being equal to 1/3 of the rate of formation of the bromine. Let's plug in what we know. So I'm going to multiply each side by 5. So my answer will be a -5/3 times that 0.039, and I get 0.0065 moles per liter per second. We have one more. So this one is comparing that bromine to the hydrogen. So we have a 6:3 ratio. So I'll go ahead and set that up. So this coefficient, that 3 turns into 1/3. Let's plug in what we know. Moles per liter times S. So I'm going to multiply each side by 6. So that's going to be 6/3 or 2. 2 times 0.039. And I'm going to get a -0.078 moles per liter times seconds. I guess it's moles per liter per second. So it would look like this. Let me just go back and fix that. So second down there. So in your homework, either question number 16 or something close to it, find a problem that's just like this and practice